And yes, it is wonderful to have Russell Menezes with us today. So Russell is the CEO and co-founder of Explore, and he began his career as a geologist. During this phase, he recognized the pervasive data management challenges within the resources sector. So through Explore, he's committed to enhancing data management procedures in the resources domain through the application of robotic process automation and machine learning. So it is going to be awesome learning from him today about the search of unrecognized minerals, a battle between Chat-GPT and extractive keyword search approaches. So strap yourselves in. It's going to be a great session. Please keep using the chat and we'll open up the floor at the end. And yes, thank you so much, Russell, for joining. It's awesome having you here today.
Thanks, Jess. So thanks everyone for attending. I can also see some old colleagues. Hi, Gina. Long time no see. So since Jess has already given you guys an introduction, I'd just dive directly into the topic. So my reason for bringing this up is I know companies have been using like keyword searches for all number of things. The simplest version of keyword searches is your Control and F that you do within PDFs. But very recently, since late last year, Chat-GPT has gained a lot of popularity, and I've seen posts on LinkedIn where people have been trying to do geoscience-related stuff with it and have been very unsatisfied. So I thought this presentation might share light on, but more on the technology that ChatGPT uses, and I can talk a little bit more about how you could use that in your project generation workflows. So since majority of the audience are geos, let's just dive deep in. Let's start with what the problem is. So John's a geologist who I worked with a few years ago in the beginning of my career, and I always like to use his name. And so what is project generation and how do explorers do it at an early stage? They go through existing data sets, and Australia has a large amount of open file data. So that's the mineral exploration reports, which sit within the various government repositories. So we have explorers, geos, or John, who reads through these reports, trying to find something something that he finds, which he thinks someone else must have missed historically. And he does that by looking at indicator minerals, relationships between different minerals, geological settings, and a number of things. But let's consider lithium, because lithium has been quite a hot topic of the last few years. So a common geological model for lithium in Australia is the hard rock type. And when explorers and prospectors look for lithium, they're often looking for pegmatites and other associated rocks and minerals like spodumene, petalite, lepidolite, zinwalites, and which are few. And so when they do that, how do these mineral exploration reports actually look like, and what form do they exist in? So this is a snippet of exploration reports taken from different government repositories and put together. And 80% of mining data is in this form. And we call this unstructured because it doesn't have any particular form. Unlike your data in Excel and databases, they can't be queried easily. They mostly exist in text form or images, scanned images of reports. They can be handwritten, typewritten, and the most common formats are PDFs, images, PowerPoints. Now, there's a lot of this data. The amount of the volume of this information is huge. So if I pull out my laser pointer and look at the small 350 square kilometer area, there's around close to 1,200 historical reports comprising almost 100,000 pages. These include scanned reports, handwritten, and all the forms we showed you previously. And so how would John go through that information? So let's take the 120,000 pages from the 350 square kilometer area. And if John has to find information on pegmatites and the associated minerals, he'll open each and every page. He'll read, analyze, and extract anything he needs. And just based on talking to several geos, they can average about 100 pages a day, but let's be optimistic and say they can do 150 pages a day, because who reads through every single page? It would, even doing that, it would take the person almost 3 years and $500,000 of the company's money to go through just this tiny data set. And that accounts for just 2% of the data. But no company ever does this because there's no business case to ever go through all the information. So companies usually pick through, find reports from operators who they think were reliable, or they might just pick random reports, assuming that every single company has the same disadvantage. But recently, with Acrobat, with OCR becoming more popular. So, by the way, for those who don't know, OCR stands for optical character recognition. And it's the feature within Acrobat PDF where you right-click on a report and you say recognize text. It goes through an image of a scanned report and converts it into text. So there's more and more companies who are trying to use the Control and F feature to search for keywords like pegmatites, lithium, spodumene, etc. But what are the limitations of doing this in project generation? The first one's obvious, that most of the legacy reports or information or most of the reports where true value consists of scanned images of reports. And the Acrobat OCR system isn't very good at digitalizing these kind of legacy data sets. Also, if you take a PDF with 10 pages, it might take about a minute or two to OCR those 10 pages. So what about reports that have 1,000 pages? Or what about your entire database, which has like close to 5 million pages? It's impossible to do that. Second, when you search for keywords, say you're looking for IOCG deposits and you want to look for hematite. What about how would you look for hematite? Would you look for hematite or hematized or hematization? Which form of the word would you look for? You can't look for all of them together, and so you might have to do it one by one. But again, within the realm of hematites, what if your hematization is spelled with a Z or an S? So would you search for hematized or hematization? But also, the word hematite can be spelled with different ways. You can spell it as an H-A-E-M-A-T-I-T-E or a H-E-M-A-T-I-T-E. So that's assuming people have spelled it correctly. But what about people who haven't spelled it correctly? Or what about reports where the OCR has failed because it's handwritten, or where there's a symbol besides the word, so the OCR picks it up as an F hematite? So there's so many different possibilities, which is why when you use a Control and F, you're getting just a fraction of the actual information that's within it. Let's look at a nickel. So say you want to search for massive nickel sulfides. You want massive nickel sulfides to be as a phrase, because you don't want massive to be on one page, you don't want nickel to be on another, and sulfides on the third. So you'd want to search for it as massive nickel sulfides as a phrase, which you can't do using your Control and F. But assume you could do it. What if the author had expressed massive nickel sulfides as nickel sulfides and massive sulfides? This is how Geo sometimes, each person would write their report in their own unique way, and a keyword search wouldn't account for all of these. And lastly, the most important one is assays. Almost every geo for every project would go through legacy reports trying to look for historical assays, because that could be something that could be the turning point, which would let them get their initial funding to even go and do more follow-on work. So say you want to look for you want to look for gold assays between 30 to 50 grams per ton. That's something you can't do unless your data is within a database, because searching for numeric ranges is impossible within documents. So these are all the limitations with just basic keyword searches. So before we go into more advanced searches, let's see what is a meaningful search to a geologist. I spoke to a number of geos over the years, trying to see what they consider meaningful. So they came back to me saying, firstly, all the geos want a good coverage of the data set. They don't want to search for a tiny fraction, but they want to look through almost all the data, and they want to include call logs. They want to include sample descriptions, which are mostly handwritten. They want to also look for text within images. So, for example, someone puts a screenshot of a PowerPoint within a report. That's considered an image, and it contains useful text, which is often not searchable. Second, after we consider data, when they do the actual search, they not only want to search for keywords, but they want to search for more complex things. They want to search for concepts. They want to search for analogs. They want to search for numeric ranges, which are assays. And the assays are not only within sentences, but they can be within images. They can be along drill holes. They also want to search through images, like I mentioned before, and tables. So that's the second important thing that's very meaningful to geo. And lastly, if we consider information within PDFs, they all relate to some or the other spatial location on the ground. And it's difficult to visualize that while reading a PDF. So it would be good if geospatial information could be integrated while searching through PDFs. So these three different sections are what make searches meaningful to a geologist. And so how can we achieve that? How can we make keyword searches a little more better? So let's introduce artificial intelligence and two sections of artificial intelligence that can do things what the simple Control and F keyword search can't. So I'm sure you've heard of these two words used on LinkedIn quite often. There's deep learning, natural language processing, but what are these things? They're actually quite simple to understand if you don't want to delve into the technicalities. So deep learning is something that is a technique that comes naturally to humans. So it's learning by example. So it teaches the computer to look at things, more specifically images, and understand by example. And natural language processing is a subset of AI where we teach the computer the ability to understand human language and to understand the meaning behind words and sentences. So just to give you an example, deep learning is what Facebook uses to automatically tag your friends on Facebook, or it's what Tesla uses to drive cars, to automate driving of cars on the road. And natural language processing is what Chat-GPT uses as a base to allow the computer to understand the intent behind the human's questions. So now going into each and every technique is beyond the scope of this talk, but I thought I'd just give you an outline of what are the different techniques that happen on the back end, which will enable a hybrid keyword search, which I'm going to talk about next. So we start off with unstructured data where you have your information within all these formats, and the first goal is to digitalize it. I spoke about OCR earlier, where you go through words and where you go through images of sentences and convert them into actual text representations. But most modern OCRs don't do a simple image to text conversion. They also apply other smarter things. So for example, the best way to explain this is take the word hematization and say you have hematization on a typewritten report, but there's a fly smudged in between the word. So if you use an older OCR engine, it wouldn't be able to recognize that word because it has the first part HEMA and it has the last few letters. But what this thing, the LSTM and the geoscience model does is it has the first part of the word, it has the last part of the word, and it will compare that against a dictionary of known words. And based on probabilities, it's able to say that that word with a low probability could actually mean hematization. And that's how OCRs when adapted to geoscience literature would work, and enables users to get much more accurate words compared to any basic OCR technique. And the second technique is processing all the digitalized text. So we go through different natural language processing techniques where we tokenize the word. Tokenize is splitting sentences into individual words. Lemmatization is normalizing those words. So say if you have hematization, hematized, or hematite, they're all reduced to the root form of the word, so they can be recognized no matter what form of the word you type. And you have other more complicated things, and all these techniques apply certain processes to the words to allow them and make them readable to the computer. And lastly, you have all this processed information within a database, and you want to apply different techniques so that the human can connect with this database. And that's where you have other deep learning techniques, natural language processing techniques, robotic process automation techniques. And this whole thing combined together allows a user to take basic keyword searches and just do much more with it than you could with just a Control and F. So let's move directly into a system. So assume we've applied all those techniques to our words. Can we take those limitations and convert them into abilities that are actually useful to us? So instead of doing this programmatically, I've used the RadExplore platform, which does these things in the background, and I'm just showing you the results related to it. So take, for example, the first limitation which we had seen, which was the second limitation, which was hematization, where we search for the word, but because of the different forms of the words, we'll have to type them out separately. But here, we've typed hematization, and we've seen that we have over seven times more results compared to just the basic Control and F search. So even though we've searched for hematization, you can see it picked up hematized and other forms of the words. If you continue lower, you can see there's hematizing and hematization, and all the different forms will be included in here. Just the thing to note is we've searched for hematization here, and just keep this number in mind. We have 1,400 hits within this database. So let's go to the second ability, the ability to recognize misspelled words. We spoke about how the word hematite can also have misspellings, either because the user misspelled them or because the OCR, for example, in this document, wouldn't be able to recognize this poor quality handwriting. So here, for the same word hematization, previously we had 1,400 results, but now we have over 10,000 results for the same database. And that's because we've applied a spelling feature to, we've applied the spelling feature to the query. So yeah, what the query does is it can search for all spelling variations of the word we are typing out. So if you see here, it's picked up the word hemorrhized, hemiter, and all of these are products of OCR of very poor quality documents. So this ability allows us to search for complex geological words and account for all the different spelling variations and forms in which they might occur. So the third one is the ability to express phrases differently, and this is for a massive nickel sulfide example. So when we type in massive nickel sulfide, I said the user could have expressed this phrase in different ways, as a nickel with massive sulfides, or nickel sulfides and massive sulfides, or many different ways which I might not even know now. But by accounting for the different ways in which phrases are expressed, we can take that simple phrase search and almost more than double the results we got. So by applying phrase expansion to our search, we've taken the keyword search, converted into a hybrid keyword search, and now you can see it's found massive nickel sulfide. That's the phrase we searched for, but it's also found different forms of that phrase. So in this one, it's it's allowed the user to add this word. So this one's nickel sulfides are commonly located above and in contact with massive sulfides. So here we know this sentence means massive nickel sulfide, but it's also able to locate this one. And the last one, which I consider the most important again, is the ability to search for ranges of numbers and combining that with the other searches. So here we're searching for the element AU with a unit gram per ton between a numeric range of 40 to 50. And we also want the phrase quartz veins to be here. And what you see is it's able to find 155 results where it's found all the different numerical variations between this number. So the first result shows you a 42.5 gram per ton gold that's associated with quartz veins. So all these abilities have now taken the basic keyword searches, enhanced it using different natural language processing and deep learning techniques, and have made it more suitable, have made it more meaningful for the geo to enhance their project generation efforts. And lastly, what NLP has also enabled us to go through those data sets, identify locations, and by geotagging every document, every search we do allows us to visualize the spatial representation of those terms within a document on a map. So, for example, we search for IOCG copper here. What the AI does is it goes through every report, finds results that mean IOCG copper, and then plot the location of the document based on either something within the text or based on the tenement. Over here in this example, it's created this heat map based on the historical tenement associated with that document. And so putting all these abilities together, let's look at a real world example. So a while ago, I was speaking to one of the tier 2 mining companies, and they told me that they were looking for lithium in New South Wales, but they were looking at a very specific type of lithium deposit. They were looking for greasing lithium deposits. So if I had to simulate that, if I had to use a hybrid keyword search to do that, we've gone within the RadExplore platform, typed in greasing lithium just to start with, and it's picked up 31 pages within all the reports in New South Wales that has these two keywords. And just opening one of the results, you can see it's picked it up from this report where it's talking about uranium mineralization in the year 91. And you can see it's saying that there are different variations. One of them is greasing. But then if you look at the conclusion, the author believes that this uranium is associated with different minerals and lithium is one of those. So within this page, it's picked up greasing and lithium, and this is something that Geo would do manually. So this is an example of a hybrid keyword search where it's not just looking for keywords, but it's doing a little more in the background. And so now that we've talked about hybrid keyword searches, let's look at not ChatGPT, I'd say GPT models. So just to give you a bit of a background on this, GPT stands for Generative Pre-trained Transformer Model. So transformer models are a type of deep learning model which, how do I explain it? So before I'll explain it a bit further, but let's look at this example first. So this is Chat-GPT. So Chat-GPT is an application that's built on a large language model, which is the GPT 3.5 model that OpenAI, that belongs to OpenAI. And I've asked it the same question. Can you tell me about greasing lithium deposits in New South Wales? And if you look at the answer, it says that it's not aware about greasing lithium deposits. And the reason it says it only has knowledge until September 2021. But if we looked at our report previously, the report was from the year 1990s. So ChatGPT was trained on all the data from the internet until September 2021. And one of the limitations was these historic reports are not on the internet. And so it wasn't included as it wasn't part of ChatGPT's training. So what it does is it just gives us a generic answer on lithium and just talks about lithium mining in Australia. So what is this GPT model? So the generative part stands for create text. So what it does is GPT models are like text generators. But it can generate text in a natural way, just like humans would speak. That's what the generative bit stands for. Pre-trained is that it's been trained on massive amounts of data from the internet. And like I said before, the GPT 3.5 model, which ChatGPT is based on, has been trained on 8 million web pages. And it has 175 billion parameters. So when I say 175 billion parameters, what that means is it's different things that can be adjusted within a model. So when I'm sure you've seen models of neural networks where you see these circles, which are nodes, and they're connected to different nodes. So they have 175 billion of those. And what that does is it allows the model to be more expressive, and which is why it sounds just like a human. So a transformer is the actual structure of the model. And the easiest way to think about that is it's similar to how our brain is structured. Transformer models is the structure that these GPT models use. And lastly, the word large language models comes from the fact that you need a lot of computational power and memory, just like a supercomputer, to be able to run these. So what are the limitations of these large language models when it comes to project generation, especially when it comes to using our own private data set with it? The easiest way to think of this is it's like a closed book exam. So ChatGPT was trained until September 2021, and it doesn't have any information after that. But then people would say, why can't we retrain it? So to give you an idea, to train the GPT 3.5 model, it cost OpenAI $4.6 million over 34 days. And that's the time and money it took to train that 175 billion parameter model with 8 million pages worth of text data. And lastly, I'm sure those who have delved into the space of deep learning, especially the image classification models where they try to classify cats versus dogs, might be familiar with the concept of fine-tuning. So when it comes to image recognition, fine-tuning allows you to add different kinds of images to data and allows you to adapt that model with a new domain. But in terms of large language models, it's a bit different. So fine-tuning does not update information within the actual large language model. And that's a misconception and a very common thing that I see on LinkedIn and other forums. But what fine-tuning does is it allows you to take a model and adapt it to different tasks. So for example, GPT 3.5 was the model trained by OpenAI, and Chat-GPT is a fine-tuned application. So Chat-GPT is a chatbot that they fine-tuned GPT 3.5 so that it behaves in that manner. So when you type a question, it gives you an answer. So you can also adapt GPT 3.5 for different tasks like a chatbot, an assistant, a summarizer. So I was speaking to Jessica earlier this year, and earlier in the chat, and she told me she feels ChatGPT doesn't sound like her. So one of the things she could do is create a fine-tuned version of herself where she would take questions and answers, create about 300 or 400 examples of them, and fine-tune the GPT 3.5 model. And if she uses ChatGPT with that fine-tuned version of GPT 3.5, it would sound just like her because it has been fine-tuned to sound like how she would based on her own questions and answers. And that's what fine-tuning means for when it comes to large language models. But what the question is, can we ChatGPT, GPT 3.5 is a closed book, is like a closed book exam, but can we open the book and show it information? The answer is yes. So take that same question. Can you tell me about grease and lithium deposits in New South Wales? So what if instead of using just the model, we open it up to the data within the digs or within the digs database? So that's the mineral exploration reports in New South Wales. Can it give me the answer? Yes, it can. And this is the answer. In the examples on the next slides, I'll show you how it looks. So how does this actually work? What we do is when we ask our AI the question, what it does is it first takes the user's query and tries to figure out what the user's actually looking for. So that's what I call converting the user query into intent. So this step allows us to understand the user's intention or what they actually want to know. In the second thing is we compare this intent with all the information within this open book, and that's the digs database. So when we compare the user's intention with the intentions in the database, it's similar to finding a match between what the user wants and what the database can offer. So once we have that, we can take whatever the user has found and send it to the large language model, which is GPT 3.5 or anything else. So it's like preparing a list of relevant information that we want to use before we ask the large language model for more information. So finally, the large language model goes through the list of potential matches that the part 3 found, and it uses that content to actually answer the query. So it's like asking the model to provide information from the books that best answers the user's query. So in simple terms, we can start by understanding what the user wants. We find the books that match that, and we send that matches to a smart model and get answers from that model. But let me dive a little bit deeper into what intent actually means. So how do you convert this into a meaningful representation that the computer can understand? And that's done using something called embeddings. So embeddings is a mathematical representation of sentences. And the way it looks like is exactly like this. So you can convert a sentence into an n-dimensional vector or an n-dimensional number. So if it's just 3 numbers, it's a 3-dimensional number. But the more dimensions you can have, the more meaning you can store of a particular sentence. And so what happens when we plot these numbers in a 3-dimensional or a 2-dimensional space? So say, for example, we've converted these sentences into embeddings and we plot it on a graph. You can see sentences that have similar meaning plot in a space close to each other. So yeah, these 3 points are talking about a boy who's walking. So it doesn't matter if he's sad, doesn't matter if he's little. But again, you have a man walking in a field, which is similar to this, but not so similar because man is still human and is still walking, and which is why it's in this area. But when we look at this sentence, a dog is running past the field, it's a completely different, it's not a human, but they're still running. So you can still see that it plots close to each other. But say we have a sentence like, can you tell me about grease and lithium deposits? That would plot in a vector space that's not visible, it'll be completely far away. And that's how the AI does its matches based on this vector embedding. So now that's a lot of information that I've given you, but let's look at a few examples with respect of project generation. But I gave you an example of a hybrid keyword search. So let's see an equivalent example of a large language model GPT type search. So again, for those of you who are on a big screen, you can see the question that I've typed is, can you tell me about increasing lithium deposits in New South Wales? So we hit search, and what it does is it goes through the database and it first finds its source documents. And based on what it found on the source documents, the large language model has generated 3 answers for us. It's also geotagged all these source documents so we know where they are related on the map. And so this is one of the answers that it's given us. It's given us recent lithium deposits have been found in New South Wales, that they are associated with LCT pegmatite zones. It's also talking about a company and their drilling program. And it's given us the assays that were found in a granite. So what it's done is it's given us an answer just like a human would. So it's gone through the source documents, found relevant bits, tidied it up, and structured it in a very concise answer. This is the second answer that it's given us. It's a little bit different, but you can see there are some similarities between them. It's both are speaking about this, and they can be from different answers. And so what I thought is, let's compare the answers between hybrid keyword searches and the large language model. So these are my observations, but I know everyone might have different observations based on their own personal preferences. So to me, the large language models gave concise answers. They were able to summarize all the results and give me a concise answer so that within 60 seconds, I know what might exist in the data. But for the hybrid keyword search, it gave me 31 pages of answers, which might include false positives. So I'd have to go through each one of those or every one of those to actually figure out whether what I'm doing, whether it is correct or incorrect. The second thing I feel is, for a large language model, even though it's given me a concise summary, the summary might not be as good as me. So it might miss out on details which it thinks are not important, but might be important to what I'm doing. So equivalent for hybrid is reading all these 31 pages might actually increase my knowledge while doing project generation on both the topic and on related topics. And that might actually help me think of something that I haven't thought about before. And lastly, which I feel the most important, is the part where embeddings don't work very well when words are not in sentences. So when the AI is trying to embed a sentence or convert it into its meaningful representation, it needs to understand the entire context of the sentence. So what happens within reports where they're just random keywords because they were labels of an image, or they were within PowerPoint presentations where people don't actually use full sentences, the embeddings will not work. And that's where the large language model won't be able to make sense of that content. But if we look at the keyword searches, because keywords are just looking at individual keywords in a document, it's independent of the embeddings and doesn't suffer from that drawback. So just based on these things, I see positives and negatives in both. But let's look at a few more examples, and maybe that might help you decide which ones you think are better, or who you might actually score as the winner. And while we go through these examples, I'd like to ask you to just see which ones you prefer. So at the end, when I'm scoring all the 4 examples, you could tell me if you agree or disagree. So let's look at IOCG deposits. And the way GeoSearch for IOCG deposits are by looking at hematization, brachiation, and associated minerals. So I've put in biotite as one of the associated minerals. I've gone in within RadExplore, within the New South Wales Digs database, put that in, and I've searched for, and I've done a hybrid keyword search. So you can see very quickly that it's picked up the incorrect spelling variations of these words. So I've typed in hematization, but it's picked up a different form. Brachiation, but it's picked up tratiated, like a completely different word. And why has it done that? If I go to the source document, you can see it's picked that up from this image. So in this image, you have you have a map that a geo has drawn, and he's drawn very well. It's rare to writing within nowadays, and you can see it's picked up hematization, biotite, and brachiation from these bits over here. So this is a place where a large language model wouldn't work. But what if we had to do this within the actual LLM type search? So we called our own LLM search Radix GPT, and this is what we've asked it. I've asked it, where can I find brachiation, hematization, and biotite related to IOCG deposits? It's gone through it. It's giving me a different heat map. Just to give you a comparison, I'll go behind. So that's the heat map from the keyword search, which may or may not include false. But this is the one from the GPT type search, where it's gone, found the source documents, and summarized that for me. And these are the answers it's given us. So it's an answer, but I feel it's not actually giving me the information I wanted. It's gone through literature that other geos have typed, and it's summarized that for me. So my intent, or I feel the geo's intent when they're searching for minerals and associated rocks, are to find other geologist descriptions or whole log samples or thin section samples where these words might exist. And then it's up to the geo who's searching to actually understand the relationships between them and make sense. And that's something this large language model can't simulate. So for this use case, I personally feel that the hybrid keyword search has done a better job. Let's take another example where we look at the traditional hard rock lithium deposits. So here we've typed in something that's one of the most common ways for looking at lithium, and that is pegmatites associated with spodumene and either petalite or zinwaldite. So here we've done the same search, and there's 9 results which have popped up. And these are the associated locations. And opening this particular report, it's picked up this typewritten document where it's picked up words on different parts of the document, but you can see that it's associated with each other. So it says that there's a pegmatite zone, and these were the associated minerals within it. And this is something that I feel as a geo I am looking for. But if I ask the large language model or Radix GPT the same question, it might not be able to make sense of this. And let's see what it does. So I say, show me lithium deposits associated with pegmatites and spodumene and associated minerals like petalite or zinwaldite. It's again gone through it and given me quite big answers. I'll stop here so you can read it, but read the answer. But just based on this, I still feel it's a generic answer that doesn't truly answer the question I want. Maybe I've not asked it in the right way, but also remember, when you use Radix GPT, it has to be meaningful. Like if you ask it something, if you just put random keywords, it wouldn't work, because the goal of the GPT is to understand the intent of your question. And this is what I feel is very difficult to convey to a GPT type search. But let's look at another example, but this is an example where I feel these large language models shine, and that is when you're asking highly technical and scientific questions. But let's look at the equivalent hybrid example first. So my goal is, the question here is, I want to look at, well, forgetting my question. Let me just go to the next slide first. So the question was, what features of the Cobar copper deposits suggest that it could have formed by syn sedimentary processes? Now, this is a deep question. It's an answer that I can't give just based on my 7 years of geology experience. So I've taken the help of another PhD geo who's worked at Geoscience Australia for 20 years, and he's helped me come up with these questions. And if we look at the hybrid keyword search, I've typed in cobar, copper, and sin sedimentary to simulate that question. Because when I typed anything else, it didn't come up with any answers. So this one's come up with 2 answers. And opening one of the reports, you could see it picked up cobar and copper here, and it picked up sin sedimentary faults here. But I don't think that this concept is related to these faults. So this is what I call a false positive, where it's found the same information, but it might not be related to each other. So if we discount this answer, it's not actually found any answer. But for the same database, the large language model has given quite good answers. So this is the answer that the large language model gave us. And if you read through it, you see that it's answered the question that you asked here. So now to conclude, I thought I'd try scoring those 4 examples. And so when we looked at that recent lithium example, I feel both gave quite good answers. So this is where both large language models and the hybrid keyword search work equally well. But when I looking for prospects or mineral deposits based on relationships and the distribution of different minerals, that's where the hybrid keyword search shined and the large language model didn't do well. And then when it came to research type questions or scientific questions, that's where the large language model shined. Now, if you total this, you'd see that hybrid keyword did better, but that's because the use cases were biased. So what I want to do is just not total these, but what I want to say is that the search type you use would depend on your particular use case. And for me personally, I'd like to have both in my wallet, because who knows which one I might need to use when. So I feel the hybrid keyword searches are suited to users who know very specifically what they're looking for, and they want to use data mining techniques easily without having to program, and use that to analyze the distribution of words and the relationship between them, and also visualize those relationships spatially on a map. Whereas large language models are suited to users who don't know what they're looking for, but they want a generic answer very quickly, and that might actually enable them to frame their hybrid keyword search. Also, it's useful for more scientific and research-based questions, and for reports where the databases consist of well-worded sentences. So what I feel at the end of this is it'd be good to do an LLM type search first, increase our knowledge, and based on this, frame our hybrid keyword search to drill deeper into the data sets. And just to conclude, if you want to give these a try, RadExplore is now available for free for certain data sets. So anyone can just go onto the website, sign up, and start using it to have a play with the free version of RadExplore. So the large language model searches are not available yet, but it would be in the coming months. Okay, thank you.